I just don't want to start back here. This is kind of where we stopped the other day. So oxidation states can, we know that transition metals can have more than one oxidation state, but in 151, what we covered were just very small bits of it. What we did was we actually looked at the most common oxidation states. These are the ones that are more stable. They're all colored in red. If we look at copper, copper can be +1 or +2. That's the more common oxidation states, but copper can also be +3. You very rarely see that. And remember, I showed you a picture the other day about with the malachite and azurite. Azurite being blue, giving you the +2. Malachite being green, giving you the +1. Iron can be +2 or +3, but there's +4, 5, and 6. Now, I don't think I've ever seen anything that has 5 and 6, but I have seen +4, and that's with pyrite. Pyrite is fool's gold if you don't know that. Manganese +2, +4, +7. We have actually seen that compound very. We used it a lot in the last chapter when we balanced half redox reactions. Chromium's +3 or +6. We talked about emerald versus ruby. Chromium's +3 is probably the more common one, but +6 gives you an orange color, and +3 gives you a green color. And then you have these other rare oxidation states. And the list goes on and on. Okay, we could have many different elements, but this is just a number of the ones that we typically find and use: chromium, iron, copper, zinc. Zinc's always +2. Cobalt, we could have done cobalt in the lab, but we don't have time for that, so we didn't get to do that experiment. But that's actually the last experiment in the lab manual. So now complexes are formed between the ion, in this case the cation, and the ligand. We talked about that just a little bit last week, so I want to kind of make sure that we are still on the same page together. So remember the metal is found inside the complex, the center. It's the center, and then the ligands are attached to the metal. And so the metals can have just a different number of ligands attached to it. It depends on how many hands it has, and that's the coordination number. We talked about primary versus secondary valence. Primary is the actual charge of the metal, and secondary is how many ligands are attached. And that's determined by the coordination number. So the coordination numbers can range from 2 to 12, but 6 and 4 being the most common. I see 6 more frequently than anything, but again, it really depends on the element, the cation that's present, and the type of ligand that's attaching to it. So there's a lot of things that go into it, but again, so if we look at this compound here, this is cobalt chloride with 6 waters attached to it. This is actual complex, and so the complex that forms is the cobalt with the water surrounding. Now the chloride ion is on the outside. We call this the counterion. The counterion just balances out the charge of the complex itself. Now water is neutral, so the charge of the complex is really carried by the metal itself, cobalt. And so in this case, cobalt is +3. So you need 3 chlorines to cancel out that +3, because this is going to be -3. So this is +3, this is -1, that's -3. So this is equal to 0 in the end. Now, what's important here to understand is that cobalt is +3, so that's primary valence, and its secondary valence is dictated by how many ligands are attached to it. So it's 6. So it's got a coordination number of 6. So if you ask for the coordination number, you look at how many ligands are physically attached to the metal, not necessarily the chloride, because the chloride itself is considered to be the counterion, and basically that is to balance the charge of the complex. All right, so that's just a quick review of what we covered the other day. I wanted to talk about that because we kind of went through it a little fast, but that's okay. I knew I was going to come back to it today. We're going to see a lot of complexes, and you'll get to see a whole different variety of ways that they're formed and the type of complexes that can exist. So this is just another picture we looked at there. So I'm going to move on from that. All right, so complex ions, all right, is a type of Lewis acid-based reaction. Remember that Lewis acid is going to accept a pair of electrons, where Lewis base is going to donate a pair of electrons. So when you look at the example below, the silver +1 ion is an acid because it has no electrons to donate. The NH3 has a lone pair. And that lone pair can be donated to the silver. Now, if you pay attention to this, there are two ammonias here, and those two ammonias form this physical covalent bond between the silver. Now, it's not that the the +1 dictates how many ammonias are attached, because the charge in this case doesn't necessarily make the difference. It's really dependent on the coordination number for that element. So silver in this case has a coordination number 2 because you have two NH3s attached to it. And now the technical term for this would be a Lewis acid-base addict, and that's because of how the NH3s interact with the silver and form their coordinate covalent bonds. Now it's called coordinate because silver in this case has a coordination number of 2, and so the coordination 2 means it's going to have two ligands attached to it. Now the overall charge of the complex is +1 because ammonia is neutral. So if ammonia is neutral, it's not going to balance the charge. So the charge of the complex is really determined by the silver ion, which is +1. Any questions on this slide? All right. So I'm going to give you, write this slide down, okay? I'll give you a couple minutes to write this down, then I'll get back to it. All right, so in this slide, we're going to talk about chelates. So chelate basically is a ligand that has more than one place of bonding. So a good example is the ethylene diamine that we see here. And if you notice that on this ligand, you have two NH2, so you have two amine groups. And so there's a lone pair here, and there's a lone pair here. If you have an extra lone pair like that, that's a place of attachment for the ligand. And so in this example, we call this a bidentate because it has two places of attachment. All right, I think of dentist when I think of this. So bidentate means that you have 2 teeth to use. So in this case, you have 2 of these lone pairs, and that's where the bonding is going to take place. Now, if you have, so like the cobalt example we used earlier, okay, so if you have cobalt with +3 charge, now the coordination number for this was 6 from the previous slide. Excuse me. So with that coordination number, if we look at this ligand, the question is, how many of these ligands will attach to this cobalt? Well, if we look at the fact that cobalt has a coordination number 6, and that this bidentate uses up 2 of those 6, that means that you're going to have 3 of these ethylene diamines attached to the cobalt. Right. So the complex would be cobalt, and I think the abbreviation is En for ethylene, 3 with still a +3 charge, because that just represents the fact that the cobalt's +3. You didn't have anything to cancel it out here. Yeah, so En is the prefix for ethylene diamine. Now we'll get to a slide where you look at all the ligands and their prefixes in just a couple minutes. So, but this is just an example of how the polydentate is interacting with the metal itself, the cobalt. So this is a whole list of ligands. All right, this table is in your textbook, by the way. So water is a ligand. We've seen that already. Ammonia is a ligand. We've seen this. And then you have these examples here. And here's your ethylene diamine we just looked at. And then you have EDTA. EDTA is by far the most common and the most popular ligand out there. So we're going to look at that in just a second. So here is EDTA. Now, if you look at the top here, it says hexadentate. Well, hexa is 6. That means that EDTA has 6 different placements that attach, and it's indicated by the arrows that you see here. And so with that cobalt that we looked at earlier, now this complex would just be simply cobalt EDTA, and you don't really have to have parentheses here. I just wrote it in there with a +3. It only takes 1 EDTA to make the complex with cobalt because of how many places of attachment it has. So here's the example with cobalt and the ethylene diamine. So you see how you have the 3 ethylene diamines attached around the cobalt. But then now if you look at the cobalt with the EDTA itself wraps itself around the metal so it can form those coordinate covalent bonds between the cobalt. Now, one thing you got to understand is that once these complexes form, they are not going to break apart. These complexes, these coordinate covalent bonds, are fairly much permanent. And so that's important because EDTA is used in some of our beverages. And the reason for that being is that they are putting them in place to remove ions that would leave a bad taste in their mouth. All right, they don't want the consumer to have a bad taste and then they not buy their products. What do? They put the EDTA in there to bind with the metals that might taste bad or give it a weird taste. So ligands are important. All right, you actually have complexes in your body that act as ligands as well. And so your iron, your heme group, and hemoglobin is a good example of a complex. Now, as we talk about geometries, I'm not going to spend much time on this, but you have your coordination numbers, and then you have your basic geometries Octahedral is the most common. So if there's one that I would tell you to remember, it would be octahedral. All right, that remember that 4 is another one, but these are two that you don't see very much, and I hardly ever see linear. We do see an example here from earlier with the silver ammonia complex, but so 6 octahedral. I definitely will make sure you remember that one, and then you have the other three. But obviously you can have this slide, so it's not like you got to memorize it for the test. You just have to understand. Now, what I'm going to do here is give you guys, this will take a few minutes, so I'm going to give you guys 4 or 5 minutes. I want you to write this slide down. I will come back and we will continue naming coordinate compounds. So we'll spend the rest of the time today on that. So y'all go ahead and take some time now and get that jotted down. I'll come back soon. All right, naming coordination compounds. Okay, so naming those complexes and then the counterions. So the first thing you got to do is determine the name of the non-complex. So that's the counterion. Okay, so the Cl would be a good example. That would be chloride. So it's not like it's a whole different thing from what we did in 151. It's just a matter of putting pieces together to get the full name. So the complex itself, what's in the brackets, that's what we're going to really talk about today. The counterions are named very similar to what we did in 151, so that's nothing different. All right, so it's the complex that we need to focus on. Okay, so when we look at the complex, now here's the thing that in the examples we looked at so far, the complex, we only had one ligand attached to the metal. And so that's pretty simple. The ligand goes first, then the metal and its charge, and you have to use the Roman numeral for the charge. Now, if you have two ligands, the ligands are written in alphabetical order. So yes, the name makes the difference in when it's wrote first and second. You can't just write it the way you see it and you want to write it. It has to go in alphabetical order. That would be the thing I would suggest you maybe highlight from here, is that the ligands go in alphabetical order. Now, again, keep in mind that you have the ligand, the metal, and its charge, the Roman numeral charge specifically. So make sure that you write the Roman numeral charge for the metal ion, all right? So now if you had silver, silver's +1 only, so you don't have to worry about writing silver's charge. But if you see iron, yeah, you better make sure you have the Roman numeral. There's only a couple transition metals that you don't use the Roman numerals for, and that's silver and zinc. So those are the only two. Everything else needs the Roman numeral. So again, silver and zinc, you don't have to write the Roman numerals for, but everything else you do. Okay, so how do we write the ligands and the name? How do we name them? So basically, bromide is bromo, chloride is chloro, hydroxide is hydroxide. So if you notice, there's a pattern here. So instead of having the IDE, and this is for the ligand specifically, not to count the counterions, remember this is only for the complex here, okay? That we're talking about the complex specifically. So the bromide is called bromo. So all we're doing is changing the IDE to O. Yo, bromo, how you doing, chloro? What up, hydroxo? Yeah, you get pretty fun with these things. Cyano, nitro, oxalato. Man, this thing is fun. Yo, just say that out. Oxalato, cuz. Cyano. Golly, I'm so sorry, people. All right, and then you get to EDTA. You should say this one 10 times. So it's ethylene diamine tetraacetate, ethylene diamine tetraacetate, okay, no. Ethylene diamine tetraacetato. Makes me think of potato. All right, get down here. Water's aqua. How generic, right? Ammonia is amine. How we know that one. Carbon monoxide's carbonyl. And then ethylene diamine is, well, I mean, how hard is that? Ethylene diamine. Wow. Can't you be any more original than that? Ethylene diamine. Nope. All right, so we get to the metals. All right, so now here's the thing. So up at the top here, so if you have a positive charged cation, or in this case complex, you don't have to worry about this table. So if the complex is positive charge, you don't worry about this. Now if the charge of the complex is negative, you say, well, how could the charge of the complex be negative if the metal's positive? It depends on the ligand. So go back up here. What's the charge on these right here? They're negative. So if there's more negatives than positive, guess what? The complex is negative. Math, right? Now, so if we look at chromium, chromium would be chromate. Cobalt is cobaltate. Copper is cuprate. Now you say, where the heck did cuprate come from? Okay, remember, this is something that you probably learned or did not learn. I don't know. It depends on your instructor. So some of the metals have Latin names. So Cu is cuprum. All right, so that's cuprum. Cu. I have no idea what's going on in my hand right now. Cuprum. All right, and so that's where cup comes from. And then so the ER gets changed to cuprate. Iron is ferrum. And I'm just giving you the Latin names here. Lead is plumbum. And it's called that because it actually looks like purple plums on a rock surface. When you look at these in nature, that's how lead forms naturally. All right, then let's see. Yeah, so the silver is argentum. Now think about it. Argentum sounds like which country? Argentina. So silver gets its Latin name from Argentina, which is argentum. And that's because Argentina has a very large reserve of silver, probably one of the largest in the world, if not the largest in the world. So keep in mind that the charge of the complex has to be negative in order to use the names like you see here. So you don't use these names for positive charge. You only use these names for negatively charged complexes. Any questions on that? All right. So looking at two examples here. So these examples are found in your textbook. So we'll look at this one first. So now before we do anything, what's Cl? It's on the outside. It's called the counterion. So Cl is chloride. So we don't need to worry about doing any more of this. So our focus is on what's inside the brackets. Now, if you look inside the brackets, you see the chromium. All right. The chromium, we got to figure out the charge on the chromium. That's the first thing we need to do here. All right, we see that we have water, and we also have chlorine attached in the complex. So chlorine is, you have one chlorine inside and two chlorines on the outside. Water is neutral, so it has no charge. So this is -1, and this would be -2. So total charge is -3. Since water's neutral, chromium has to be +3 in order to balance out the overall charge of -3. So we get that to be equal 0. So the charge of chromium is +3. So that's the next thing I do. Now, what I want to do after that is, now I want to look at the ligands. So let's name the complex. Okay, so water is aqua. Now since Cl's inside, it's called chloro. We talked about that on the previous slide. So what we do next is we figure out, we already figured out the charge of chromium is +3. So now we get to put these in order. So aqua is A. A comes before C, so aqua is going to go first. Now, if you look, you have 5 aquas. The prefix for 5 is penta. So you have penta aqua. Now, if you see right here, so it's penta aqua. Now, notice what they did here is they took off the A. So aqua is AQUA, but aquo, because it's in the complex, so you put that O on the end, chloro. So penta-aqua-chloro. So if you look at the chlorine, there's only one chlorine. You do not have to use the prefix mono. All right, you only have to use prefixes 2 and higher. So in this case, it's penta-aqua-chloro, chromium 3. Remember, the ligands go first in alphabetical order, and then the metal with its charge. So here you have the ligands underlined in red, and then you have the metal with its charge. And here's the charge of +3 as we determined from the complex. Now to finish this off, so what you have is pentachlorochromium 3, that's the complex. And then you put a little space in here that indicate that now the next thing that comes in is your counterion, which is chloride. We did not use the chromate because the charge of the complex is +2. So if you were thinking about the fact that we talked about chromate in the past slide, we don't use chromate because the complex is positive already. We only use chromate, the ATE, when the charge of the complex is negative. All right, so the next question here talks about the naming of this complex and this compound. So here we have charge of potassium on the outside. So notice over here we had chlorine. In this example, we have potassium. Now potassium is +1. There's 3 of these. That means that this is +3. the complex comes after it, so that must mean the complex is -3. So that's a good indicator that the complex is going to be negative. So this is going to be using the rule where we have to look at the Latin name for iron. All right, so let's do a couple things here, because potassium is potassium, that's done. So let's look at the complex. The CN is cyanide, but in the complex is cyano. There's 6 of those, so that's hexacyano. Now Fe is ferrate, all right, because we said ferrate because of the fact that ATE comes from the complex being negative charge. Now the last question we have here is, what's the charge of the iron? So you have 6 of the cyanides. The overall charge is -3. So you set that equal to -3. Cyanide is -1. There's 6 of those. That means that this is -6. What -6 equals -3? Well, X has got to be +3. And that's the charge of the iron. So we have iron with a +3 charge. So you have hexacyano, ferrate 3, and the 3 comes from the fact that the charge of the iron is +3. Now, to fill out the rest of this compound's name, so we have K in the front, so this is potassium hexacyanoferrate 3. And you can see the name being wrote out at the bottom down there. But remember, the counterion is first, and then you have the complex, and that complex in this case consists of the cyanide and the iron +3. So the first thing you should always do is figure out the counterion and determine if the complex is positive or negative. If it's positive, it just goes straight through. If it's negative, remember you have to switch the name of the metal to that ATE. So like ferrate or cuprate or molybdenate. All right, so these are just examples, and that goes back to this chart that you see here. So there's a few charts that you probably want to print off and have available as you are working on naming these compounds. Any questions?
Would, if like it's a neutral molecule right there, would that just count as positive?
When you say neutral, what part are you talking about?
Like the charge of the molecule, you were saying you would use those specific names if they were negatively charged, right?
Yeah, you're talking about the complex. The
Yeah, the
complex.
complex.
Yeah, the complex will be positive or negative. All right, it won't. I don't think the complex is going to be neutral because you normally are going to have a counter ion that balances out the charge. So what you need to do is figure out first, is the charge positive or negative? Is that what you're asking?
Yeah, yeah.
Okay.
Okay, so you really just won't have a neutral one.
No.
Gotcha.
Now the whole compound will be neutral, but the complex itself will be either positive or negative.
Gotcha.
All right. Now there's a practice set of on Moodle. So if we had more time, I'd go through a lot more examples. But so look on Moodle and get that practice handout that I put on there. There's 2 different sets of naming. I did put the answer key on there too, so you should be able to work with it. And if y'all have questions, just make sure you ask me. All right, I might try to do a supplement video with this after I get done. I got at least one video to make for the crystal field theory. All right, so let's talk about structures here. This is the last thing I'm going to discuss today. All right, isomers are molecules that have the same number and type of atoms, but they're different because of the way they're attached together. So when we talk about isomers, if you take organic chemistry, you will get to deal with isomers a whole lot more there than what we're going to deal with here. I don't deal too much with geometry, but this is a good little chart to have. This is in your textbook, and it's also in the PowerPoint if you want to download it. So this is just a little flow chart that helps you to see it and try to, put it together as to what type of geometry you're dealing with. All right, so as we talk about isomers, the linkage is the next thing we can look at here. Linkage is depending on where it's attached to as far as the ligand goes. So you have two different examples here with the nitro groups that you see. So one is nitro and the other one's nitrito. You don't have to worry about why the name changes. It changes because of the way the attachment is to the ligand. So if you look at this one here, all right, you see cobalt attached to the nitrogen itself. So that would be nitro. Now, if you look at the next one here, the cobalt is attached to the oxygen versus the nitrogen. So that would be nitrito. And so the color changes because of the attachment of where you see it on the cobalt and the nitro group. So yes, placement of the attachment to the ligand makes a big difference in the colors we perceive. This is just examples of different ways that you can attach. So this is thiocyanate. Remember we talked about SCN with the equilibrium lab with iron. So the iron bonds with the sulfur here versus the nitrogen. All right, so we said iron thiocyanate. So that's where the bond forms here. Now, if the iron were attached to the nitrogen, it would have been iron isothiocyanate. That would have been different, but that's not the case because our iron bonded with the sulfur instead. So it gave us a dark red blood color solution. All right, cis and trans is dealing with whether the ligand is right beside or if it's across from each other. So cis is right beside each other. This is where they're pretty much touching each other, holding hands. All right, trans is where they're on the opposite sides. Okay, that's the easiest way to remember this. So you can see, I like to think about this AABB. So I just think about AABB being the cis, and then trans would be ABAB. Do y'all see how it rotates around for the trans? Do y'all see what I'm talking about here?
Yes.
All right, and then over here it'd be AABB. Just a quick way of remembering what's cis and what's trans. All right, another example of cis and trans. If you look at the center, you see the cis, AABB, and then if you look over here, ABAB. So don't worry about the ones that are on top and bottom. This is an octahedral structure, by the way. So remember I talked about earlier that octahedral is the most common example. This would be examples of tetrahedral because you have 4, 2 and 2, that makes 4. But here you have 4 and 2, that makes a total of 6, and that's octahedral. All right, but keep in mind again that the ones on top and bottom does not make the difference. What makes the difference is the central portion of the complex. Now, so looking at this, this gets into just more or less observational type isomerization. So when I say observation, it's how you perceive the ligands and the way they're attached. So FAC-MER is how I say this. FAC is representing face, but I don't know exactly how. I guess it'd be face-MER, but whatever. So MER means meridian. Think about the prime meridian. It runs from north to the south pole, and it runs. So I think about this. Can y'all see the meridian here? If you were to have a big sphere, this would be running straight from north to south. Can y'all picture that?
Yes.
Kinda, yeah.
All right. Now, if you look here, you see how all three of these chlorines are pretty much against each other. So if you draw a triangle, you have a face right here. And if you look at the other side, you have a face there. Now, we don't look at this here. We just focus on the blues and or the greens. And if you look at the blues here, they are in that line as well. that represents a meridian. So again, it would probably be a good idea to come back through here, just kind of, and just take some general notes, just to make sure you keep that straight in your mind. Now, optical, we don't do much with optical, okay? I'm not going to spend much time here. But if you guys will do me a favor, hold out your left hand and hold out your right hand in front of you, all right? And you're all aligned right down the middle of it, all right? If your right hand was looking into the mirror, it would see the left hand, all right? But if you take your right hand and you put it over top of the left hand, your thumbs will not impose on top of each other. So optical isomers are ones that are mirror images of each other, but as soon as you try to put one on top of the other, they don't fit together, and there's never any way that your thumbs will lay over top of each other because they're non-superimposable. If they were superimposable, they would match up perfectly, but that's not the case here. Does everyone understand that?
Is that the same as an enantiomer?
Yeah, very similar. Yeah. Yeah. So that's all I'm going to talk about with isomers. I'm not going to spend any more time on that because that's not needed here. We don't spend too much time on that. So, all right. What this does, it gets us into our last little bit of topic here. So, colors is important. And we use some of the equations from light and quantum mechanics we talked about in 151. So the next few slides will be stuff that you're going to have to go through. We get into what is called crystal field theory,